we can get it started. Okay. Uh, okay. So hello everyone. Welcome to this Georgia Tech LiDAR seminar series, and we are very glad to have Professor Wins Kurtz. I hope I pronounced your name correctly.
Yeah,
Joining us. And I mean, I can say something, more about, Win's work. We have been actually following his work for quite a long time. This can go back to his, PhD time on the signal temporal logic work, and then go to more like, I think, trajectory optimization, especially solving some of the contact problems. And then I think today he will talk about his more recent new work I think on the generative models, which is very exciting. I think a wild variety of exciting works, in the robotics community. So that's very exciting. And just a little bit more, information about Wins. He's now just start a new professorship at DePaul University in School of Computing in Chicago. And before that, he I think worked at TRI for these large behavioral models, which is very exciting. And he was also a postdoc at Caltech, and he received his PhD from University of Notre Dame. Um, and he received multiple best paper award, RSS, core, humanoids. This is all, the top-notch robotics conferences. So that's, definitely a good recognition about his research work. Um, so with that, let's welcome Vince, and we all look forward to your talk today. Thank you for joining us.
thank you. Thank you for the very, very kind introduction and for inviting me here. I'm really been looking forward to this. Likewise, I've been following your group for a long time, and I know you do really awesome research. So I'm really excited to have a discussion. I'm happy for this to be as interactive as you like. I know that's sometimes a little awkward on Zoom, but please feel free to interrupt. Be persistent if I don't hear you at first. There is a little background noise here, but we'll also have some time for questions at the end. So what I'm going to talk about today is stuff I've been working on recently. Most recently, I was working on some of this at Toyota Research Institute, where I was for the last year, and some at Caltech before that. So today, first, we're going to talk big picture, what's happening in robotics largely, and talk about the data gap. Um, and how then the meat of our talk is going to be trying to develop methods, particularly based on simulation, to close that data gap. And that means improving our simulation quality and figuring out new techniques to actually use simulation to close this data gap. So first, some background. You probably have your fingers on the pulse of what's happening, big picture in robotics, but just to recap, I think our big headline is that generative AI for robotics is starting to work. We're not at the point of ChatGPT for robotics yet, but there are early signs that we're really getting there. Um, and the general procedure that is working for people is this. You collect demonstration data manually via teleoperation or motion capture or something. Then you train a generative model. Usually it's diffusion or flow matching. There are other architectures available, but you're training a model usually in a supervised way to imitate your manually collected demonstration data, and then you deploy the trained data on the robot. So diffusion policy was the sort of the first one of the first things to come up with this. Now people have different varieties, many variations on this sort of pattern, but this is really working. And it's working so well that it has sparked massive industry investment. So big companies, DeepMind, Figure is worth like billions of dollars at this point. Boston Dynamics. These are just a few of the um, big companies who are investing. Uh, Venture capital is in on this now. This imitation learning is really really hitting the big time here. And it scales in a principled way. So one of the things that TRI did over the last several years is really dived into a very scientific sort of study of this sort of process, which they call large behavior models. And the idea behind a large behavior model is instead of just training for a single task, you collect a bunch of training data for a bunch of different tasks and combine that all into one mega huge policy that you hope is going to be more effective than a single policy task. And largely what we see is that is the case. The more data you add, so like the sort of brown curve here is all the data versus at the bottom, the gray curve is single data and everything in between. The more data you add, the better it becomes. Now, that should feel kind of obvious, but we didn't know for sure whether that was going to be the case or whether you're going to get weird ups and downs as you add more training data. It seems pretty clear that these things do scale in a nice way. So that's good news. There is a problem though, and that's what I'm calling the data gap. So what do we mean when we say the data gap? So we can think about the amount of training data in terms of time. So for this TRI project, they collected about 500, 600 hours of training data. So that's represented by this small red dot. Now, there are other sources of training data. So the OpenX embodiment project collected about 4,000 hours of training data. This slide is a little out of date. I'm pretty sure physical intelligence has collected more data by now, but at some point around the Pi 0 mark, they had about 10,000 hours of training data. And that's a lot. That's a lot of manual effort. That's, high quality manual demonstrations. If you think about something like GPT-2, this is GPT-2, right? This is like an old school, early days of language stuff. The rough equivalent is some 500,000 hours, assuming so many words per minute. If you look at a more modern LLM, like Llama 4, we can't even fit the amount of training data in our bubble on the page. So in robotics world, we're still playing around with these tiny little dots, smaller than the early days of language processing. So we still have a long, long way to go if we need anything close to the data we get to train a ChatGPT or a Gemini model. So what can we do about this? We could hope that we need less data. That's one option. It's not clear how the data demands of robotics versus language modeling map to each other. We could hope for a data flywheel. So this is what a lot of companies are betting on. Betting that if you deploy commercially and you get a product out there that's good enough for now, then you have your robots in a bunch of homes or a bunch of factories, and then you can start collecting data somehow. It's not totally clear always how, but then that becomes a virtuous cycle, and you get more training data, and this balloons. You could look at video. This is a cause of a lot of excitement for different people. If you can somehow take all of YouTube and process that in your training data, there are lots of demonstrations of people doing things and physical interactions. And so that could help close this data gap. But the last tool, and the one that we're going to talk about today, is simulation. So in robotics, we have models. Our models are not perfect, but we know that they're often good. And one of the big models we have is simulation models. So can we use model-based design? Can we use simulation to start to close this data gap? And so that's what I'll talk about today. For the first part, I'm going to talk about our recent work at TRI doing error-controlled robotics simulation. So this is all about improving the accuracy of our simulations. A lot of this is motivated by that large behavior model analysis stuff that TRI did last year. And so to get those systematic scientific results showing scaling laws, we need to be able to evaluate policies. And evaluating policies on hardware is hard. Lighting conditions change, your operator changes. As I'm sure you all know, robots can be finicky, and to get a good strong statistical evidence, we need a lot of samples. So a good way to get around that is through simulation. So our main use of simulation for the LBM paper was evaluation. So this is now released as an open source piece of software. You can run it yourself. There are about 49 tasks, carefully curated assets that correspond to real things at TRI. And it's simulated in Drake. So this is a really cool project. A ton of people, really great engineers put a lot of work into this. Definitely check it out if this is something that you're interested in. However, if you're in robotics, which most of you I'm sure are, you have probably seen ideas like this, that simulation is doomed to succeed. And often if you write a simulation-only paper, the reviewers will come back and reviewer number 3 will say, instant reject, no hardware experiments. This is just simulation. I don't believe you. And so this is definitely a long-standing, widely held belief in robotics that simulation is doomed to succeed. It cannot be made sufficiently realistic. It has artifacts. So why is that, though? That's kind of unique to robotics. Other fields use simulation all the time. But in robotics, our simulations have this scary quality to them. So is it just that our models are bad? Is that our rigid body dynamics are wrong, our contact models are wrong? A big reason simulation is bad, you hear a lot, is that the contact model is soft. And if only we could have rigid contact, truly rigid contact, then we would have sim to real transfer and that sort of thing. So is that the case? Or is this some fundamental limitation of using a computer? You're in digital, discrete world, whereas the true physics is continuous time. Is this just something we're never going to be able to get around? And so this is not just like some hypothetical thing that's the field's, consensus, but it's not really true. Robotics simulation is really unreliable. Even really good, well-tested, with lots of developers simulations, which I consider Drake to be such a good simulation, can get wild results in certain situations. So here's a scenario simulated in Drake, inspired by some of our LBM eval stuff, where a robot is dumping this mug and spatula on a dish rack, and you see the spatula stabs into the dish rack. These sort of thin objects, especially those wires on the dish rack, are really difficult to simulate. And it can even get worse. Like we could try and drop the spatula on this thin-walled container, and then it stabs into the container and starts to get all sorts of wonky things. Obviously, this is not good predictive validity. Oh, we don't want to make scientific conclusions from this kind of simulation, and it just gets worse and worse. The answer that I want to propose to this question of why is robotic simulation unreliable is that the techniques we're using for robotic simulation often descend from graphics and game physics. Game physics is really good. It's good at speed. It's good at throughput. You want your game to run smoothly. You want to run fast on as cheap of hardware as you can. It's not good at physical accuracy. And that's fine. That's what game engines are designed for. When I'm playing this Lego game, I don't care that the barrel slides in an unrealistic way. I don't care that the inertial properties of each piece are perfectly correlated to the real world, or that the contact interactions between my feet and the character's feet in the ground are perfectly realistic. That's okay for games. But for robotic simulation, that's really not what we want. We care a lot about the contact forces and higher resolution sort of things. So robotics uh, physics engines, simulators, have often in the past taken our inspiration from the game development. There is another option, though. There are a whole nother set of engineering grade simulation tools. They're used for circuit simulation, they're used for mechanical systems, for fluid dynamics. These are often highly, highly tested pieces of software. They're usually commercial, they're used at big companies. And they're very focused on physical accuracy. They're really interested in verifying and validating their simulation model, so you can really get good error bounds on modeling error versus numerical error, and really understand when your simulation is going to be good and when it's not going to be good. On the other hand, these simulators are not fast. If you want to try and simulate a robot using one of these more engineering grade tools, it's going to be very slow. And in robotics, we have a lot of demands on our simulation. We want to be able to run fast. We want to be able to run faster than real time. We want to be able to teleoperate. We want to be able to train an RL policy and run 1,000 of these in parallel, also much faster than real time. So our engineering grade tools are not quite what we want for robotics either. So over the last year, I was working with the Drake team at TRI. And so Drake's big picture goal is to combine the best of these two worlds, use some engineering grade tools to get accuracy, as much accuracy as we need, while also meeting our real-time requirements of robotic simulation. Drake is open source. You can try it out. Just at a high level, for geometric information, a big strength of Drake is the hydroelastic contact model. So again, this is a middle ground between the point contact model that you would use in a game engine and a full finite element analysis like you would use in engineering grade simulation. But it's really good for modeling complicated surface type interactions like you would use for manipulation. For the physics itself, this is similar to other physics engines like MuJoCo, but with some slight differences. So we formulate a convex optimization problem to solve for the state at the next time step. This convex optimization problem is based in this irrotational contact fields theory, which gives you some nice guarantees and properties. This is a convex problem, so it's always guaranteed to converge. So contact and simulation in Drake. There's some good things and some bad things. So the good things is that the contact model is fairly realistic. It's not finite element, but it's a good deal better than point contact. Because the problem we're solving is convex, you're guaranteed to converge two very tight tolerances. Drake really is very strict about convergence tolerances. You never stop iterations early. If it doesn't converge to your specified precision, you get an error. It supports large time steps. That's a big benefit of convex solves. We can take these large steps. That means faster simulation overall. This is huge. It's consistent. And so that's an irrotational contact fields thing that's in the last couple years that's been added to Drake. Other simulation engines don't necessarily have this. So you solve a convex optimization problem, but you have some artifacts that don't disappear as a time step goes to zero. The convex formulation in Drake does have artifacts, but those artifacts vanish as the time step goes to zero. It's still not perfect. It's a good solution. It's not perfect. So we saw some examples of bad simulations earlier. Here's another weird things are going on with these forks. The big one is sensitivity to time step selection. So when someone has a problem with a Drake model and it's doing some weird physics, the number one thing you say is, have you tried a smaller time step? And 95% of the time, that solves the problem. Related, you have convexification artifacts, and those artifacts diminish as your time step gets smaller, but they grow as your time step gets larger. And that can lead to all sorts of pass-through, like we saw before with the spatula, rattling like we see here, and so on, these sort of artifacts. What's a solution? Well, we can look to the engineering grade simulators for inspiration. Instead of discrete time, fixed step things like game engines and most robotic simulators do, our engineering grade simulators use error-controlled integration. So what is that? When we do error-controlled integration, we start with our ODE representing the system dynamics, and we want to integrate this, numerically find a solution. So how do we do this? First, we propose a step, some time step delta t, and it's going to have some error with respect to the true solution, which we're showing in red. So we guess a step. Then we come up with an error estimate. So an estimate of the distance between the true solution and our first guess. Now, we're never going to get the true error, but we can approximate this by using a higher order estimate of the solution. And so the distance between the two gray points there is an estimate of the distance between our original guess and the red line. So we use the error estimate. This is our error estimate in some norm, and we use it to adjust our time step. And so our standard rules, this is like the basic idea, but lots of heuristics to design the next time step so that we maintain a desired level of accuracy. So this epsilon ac is a user-specified accuracy parameter, and you're trying to always keep the error below that accuracy. And if you don't, you reject the step and try a smaller time step. That's the error-controlled integration idea. And then you continue. You go on like this, and you have a rigorous bound on the one-step integration error.
Hey Vince, I have one
Yes,
question about that. I'm just curious how that compares. I know that some of the like Runge-Kutta solvers and like MATLAB and stuff can do that sort of adaptive step size. Is it a similar thing where it's adapting due to
it's
error?
exactly this.
Okay.
It's exactly that. So if you do RK45 in MATLAB, it probably has an embedded error estimate. So that's your higher order thing, and it's doing this for you.
Okay,
Yeah,
cool.
very good.
Thanks.
So yeah, pros of this thing. This is known technology. It's in MATLAB. It's pretty established, this error controlled integration stuff. You automatically get time step adjustment. You can get some error guarantees. No, that's not guarantees that you're matching the true solution exactly, but it's one step error, and it gives you some confidence that your solution is more accurate. This is the big one. It allows you to decouple numerical errors from modeling errors. We always know that our robotics models are going to be wrong. We don't have truly rigid dynamics. Our contact models are going to be wrong. The inertia matrices that you write into your URDF are just approximations. There's always going to be modeling error. But when we think about simulation, we want to decouple that modeling error from numerical errors that are just due to the solver. And so error-controlled integration provides a way for us to bound our numerical errors. And then we can look at trajectory data or whatever and be confident that what we're looking at is modeling error and not numerical error. Again, this is a proven technology. There are textbooks written on this. It's standard stuff. Problem is, when you go to use RK45 on a robotics problem with rigid contact, it totally chokes. It's really bad. The steps get really, really small. The simulation is painfully slow. it's basically unusable. So the approach that we took is to try and take the best of our discrete time convex solvers and error controlled integration and put them together so we can have the best of both worlds. So this is what we're calling scenic convex error controlled numerical integration for contact. And the basic idea is pretty similar to general error controlled integration. So we're going to propose a step, but when we propose a step, we're going to use the irrotational contact fields idea. So we're going to solve an optimization problem, a convex optimization problem, to get the state at the next time step for some delta t. Then we need an error estimate. So this is the tricky part. We tried many fancy things, interesting things, higher order schemes, embedded techniques. What worked the best is the simplest thing, which is take 2 half steps. So you compare your 1 full step with 2 half-size steps of delta t over 2, and that provides your error estimate. Another thing we found out is that if you put your error estimate on the full state, things are worse than if you put your error estimate on configurations only. So why would we want to do that? If you have your full state in going into this error, you have velocity jumps as you make rigid contact. And that results in spikes in the error. If you just define your error on configurations, then things become smoother. You can take larger time steps. This also has a nice effect of being able to, you can think of this error estimate as a length scale. So if I have rigid bodies moving up and down, then that error estimate or my accuracy I can think of as something that has units of length. So my accuracy is 0.1 millimeters or something like that. Then we adjust our time step as usual using standard techniques. That's the whole scenic idea. So again, benefit for the user is that you don't set a time step. That's a big pain point. You want as big as possible, but if it's too big, you get artifacts. Now you specify an accuracy, and the solver decides the time step for you automatically. And again, we have our accuracy and our error can be interpreted as a length scale. So here is our data comparing with different integrators. So we got a cylinder that falls on the ground. This is like a peg wedged in a gripper. This is pretty hard for some standard integrators. This is Franca arm waving a Cheeto box. This is soft clutter, so you can kind of see that the balls are overlapping a lot. They're super squishy. They're easy to integrate. This is the same thing but hard, and some of them are boxes. On the bottom, these are work precision plots. This is a standard way to measure integrator performance. So on this side, on the y-axis, is some measure of work. So in this case, this is the wall time that we measured to run like a 10-second simulation, normalized to 1 second. I forget what the times are. And on the bottom is our accuracy. That's our epsilon that we requested. And so in the ideal world, we'd want really tight accuracy. So it's like 10 to the minus 6 over here and really fast. So we want to be in this bottom corner. Now, of course, as you tighten the accuracy, this integrator is going to do more work. So the slopes generally go this way. And so we're comparing scenic with dense and sparse algebra. That's our blue circles. That's our proposed approach with a bunch of standard error-controlled integration techniques. So implicit Euler, RK3, and semi-implicit Runge-Kutta method, and a Rosenbrock method. And so this is a log plot. You can basically see on some of these softer, easier examples, the other integrators actually do okay. But they're generally, between half and 2 orders of magnitude slower than our proposed approach. By the time we get up to this hard clutter example, which is more on the scale of what a normal robotic simulation wants to see, almost all of the other integrators don't even finish. I had a 100-second timeout, and I just quit after that for a 1 second simulation. We can
Quick
also take,
question.
yes.
What's the difference between the dense and sparse? It's just the
Oh, good,
manually
good.
designed. Yeah. Okay.
Yeah, so all of our um, baseline integrators use dense algebra. Um, for our solver, we have the option of we implemented sparse algebra so that the Hessian is sparse. And so we use a supernodal Cholesky
Okay.
uh, solve
Makes sense. Yeah.
for that. So yeah, the solid blue, the dense is just to be more fair to the other integrators. And you can see on these examples with lots of different objects, then you have some interesting sparsity that the solver can exploit. And so the sparse solver is better on those examples. Whereas over here, there's not really much difference. Good question.
Okay. Sounds good.
So we also compare with other robotic simulators. Um, there's a lot of asterisks to this kind of comparison. The first asterisk is this is only looking at wall time. And that is not necessarily the best thing to measure for simulation. So things may be more or less accurate and have higher or lower wall times. But basically, the takeaway is that we're on par. Even though we're doing error control, which is these bars, we can be on par with other CPU-based robotic simulators. We also threw in the GPU ones, Isaac Genesis and MJ Warp. That should be taken with an even huger asterisk because this is just a single simulation, and that's really not what those techniques are designed for. But the high level takeaway is that even though we're doing error control, we're still on par with what you can get on the CPU with other robotic simulations. Obviously, as you tighten the accuracy, things get slower. We're at a very loose accuracy that you can run the simulation faster. There are also a lot of fun new things that we can do with these capabilities. Just to establish some notation, when we're integrating an ODE, we can do this explicitly. This is like a forward Euler, which is very easy to implement, but is bad. We don't really want to do that for anything serious. A better thing is to do this implicitly. So now you have x n plus 1 on both sides of the equation. You need to use Newton to solve this. It's a little more complicated, but better stability properties. Now, in our robotic simulation, we have our multi-body dynamics, and then you also have other stuff. You have your controllers, your planners, whatever. We do implicit integration. All robotics simulators do for the multi-body dynamics part. But when you connect a stiff external controller, like a PD controller or an inverse dynamics controller, most of the time, if you're just writing it out yourself and not using the solver's special bindings, that gets integrated explicitly, so it's less stable. What we can do in Scenic is integrate this component implicitly as well. And I won't go into the details on how we do that just for the sake of time, but the end result is that we can crank up the gains on an inverse dynamics controller. So this is the proportional and the derivative gains are the same, and we can crank them up to just absolutely ridiculous values. I don't know why you would ever want 10 to the 7 as your derivative gain on an inverse dynamics controller. Don't ever do that. But if you wanted to, you could, and the simulation would still run, and it would just be very, very stiff and stable. We can also model static and dynamic friction in a more principled way using this error controlled approach. So we basically interpolate between our dynamic friction and our static friction. This is a friction force. This is as a function of tangential velocity. So here's our little toy experiment showing that here's a block, you slowly lift it, it's in stiction, so static friction, and then when it starts to slide, it really slides fast because it gets out of that regime, and now you're in dynamic friction mode. So in the old days, in old Drake, we couldn't really match this. We could match the slide angle, but then we only have one friction coefficient, so it slides slowly. Whereas if we use scenic and we use two different friction coefficients, we can tune those so we get a result that looks just like the real world. We also did a more fun sim to real experiment where this is a dish rack example where I pulled those horrible artifacts from before. So we teleoperate the robot, drop all this junk into a bin, and then eventually play back the same thing in simulation. And we don't get horrible artifacts thanks to error control, adjusting the time step as you go. So obviously you can see that the trajectories are not exactly the same, and that would be unrealistic to expect them to be exactly the same. We have modeling errors. There's sort of some chaotic dynamics going on in this simulation, but at least the spatula is not stabbing into the dish rack. And so that's what we're happy with in this experiment. In contrast, if we look at on the bottom, what we would have to do in a fixed step mode, we would have to make the time step very small in order to eliminate all of our artifacts. And at that speed, it's much slower than real time. Whereas if we are using error control on the top, we can run much faster than real time and also eliminate our artifacts. So you saw better pictures of artifacts before, but this is just sort of some of the past three things that we can get that is undesirable. Any questions on that before I move on to using simulation? Okay, so this is actually earlier.
With one quick question. I think this is great. I know TRI put a lot of effort on the simulation team, but I guess the most of the effort is to provide a high fidelity simulation, and then you can collect the simulation data to train larger models. But on the other side, I know trajectory optimization used to be like, I think, the top one of the big topics, maybe many years ago, I guess. But I guess I wonder if any of these new, contact models and, better numerical simulation tools have been integrated to solve, trajectory optimization in a better way. Is there any effort along this line, or it's a sort of, just
Great question. That's something I'm definitely interested in looking into in the future. But yeah, this is very new, so we're still landing scenic into Drake. But yeah, definitely, I think that's a promising line of research for sure.
Yeah, I think if we can solve TO problem faster and more accurate, I feel that's going to be a big win.
For sure.
Yeah. But I guess internally at TRI, a lot of effort drawn to the large behavior models and
yeah, internally for sure. I mean that is what's been working, and they have the resources to pursue it aggressively.
Yep.
Can I ask one question?
Yes.
So you talk about using simulations to collect data. So I was wondering, like, in the real world, like situations, for example, if you actually want to put robots in people's home, how, like, what are the scenarios? Like, how much in like problem instances you can actually cover with simulation? So, like, can you actually simulate or like 90% or how like a portion of the actual task that the robot will encounter so that and then you can maybe scale up those data so you see like good performance. So
Yeah,
that's my
that's a
question.
great question. I don't have like a number answer for that. Definitely simulation is getting better and better, and it's reasonable to expect that it'll continue that way as people invest in it. There are also some things that we're not very good at simulating right now. So the big one is deformables. So, right, like cloth, rope, there's some limited support for that in Drake now. It's getting better all the time, but we're still learning about the best ways to simulate those sorts of things.
So like for example, is it better? So I just this is one idea. Also, I heard this from like Dieter Fuchs. So is it better to maybe using simulation to collect data, focusing on maybe just one toy problems, for example, manipulating like the blocks, or maybe just simply just kitchen, and like in those cases, we know like a simulation can do well, and then we can scale up data, and then we can see maybe potentially scaling law before we actually start to cover multitask or yeah. What do you think?
Yeah, I mean, I think it's good to use the right tool for the right job, right? So definitely simulation we're pretty good at rigid contact at this point. So if you've got rigid bodies and you have a good model, it's a good choice.
Okay, okay, thanks.
Good questions. Okay, running a little late on time, so I'll go through this relatively quickly. So this is stuff I worked on earlier, basically, how do we actually use simulation? So this is not with error control. But what we're really interested in is all this diffusion stuff. And of course, I am very interested in trajectory optimization and optimization. So can we use diffusion ideas to solve optimization problems? So in diffusion, we want to sample from a probability distribution, and we sample noise and then take Langevin dynamics, where you have a score or a neural network approximation of the score, and that's how you generate your samples. Can we use this for optimization? Sure, why not? This is a long-standing idea. Have your cost, and then you have a probability distribution like this. So it's proportional to the negative exponential of your cost. And what does that look like for different values of sigma? Well, it's basically the cost upside down if sigma is 1. But the cool thing is that as this sigma trends towards 0, all your probability mass collapses on the global optimum. So that's cool. So then we can try and sample from a sequence of these things and bounce ourselves out of local minima and collect our samples in the global minimum. Basically, pretty cool. What about constraints? In robotics land, we care a lot about constraints. We have dynamics constraints, manifold constraints. We have safety and limit constraints. So can we add these? I'll go through this very quickly, but did some work on this. Basically, yes, you can add equality constraints. We care about that a lot for trajectory optimization type problems. How do we do that? Well, you start with your cost. Gradient of the cost, that's the same old score that we had before. You can also add a penalty. This is a gradient of a quadratic penalty on our quality constraint. But the key thing is to use Lagrange multipliers, which also flow according to an ODE, and you add them in this way. It looks a lot like an augmented Lagrangian. It's inspired by some earlier ODE-based optimization stuff, but now you can flow this just like you had your Langevin dynamics and do this optimization with equality constraints. So this is a pendulum swing up. You maybe are familiar with the eye-shaped thing. So the dynamics the dots are scattered everywhere. It's dynamically infeasible. But then as this process goes along, our dots line up with the dynamics and we get an optimal solution. Inequality constraints are trickier. I won't go into any detail at all here. We had a really fun project with JPL trying to exploring different ways of adding inequality constraints, and did some experiments in the Mars yard. Basically, we can improve safety of a pre-trained VLM type thing, while also only modestly reducing the goal success rate. Not the most satisfying results, in my opinion. So it's possible, but in both of these methods, there's significant parameter sensitivity. So I think handling constraints in this kind of problem is still in a really good, clean way. That's still open research for sure. And a big thing that I got annoyed by, especially with the equality constraints, is second order convergence. So when we solve optimization problems, usually we use Newton's method. We converge very quickly, second order convergence. Our Langevin dynamics with noising, that's basically gradient descent. It's first order. There's very little reason to think that's going to converge very, very quickly. And indeed, it doesn't. So this convergence look at these iterations, like 50,000. That's a lot of iterations to get a constraint violation that's only like modestly okay. Here's another instance of parameter sensitivity. So if our penalty parameter is high enough, yeah, it converges, but if it's too low, we get diversion. So there's still research needed there. Another big question I've been interested in, and I know we're running low on time here, is MPC and trajectory optimization. So in my PhD, I did a lot of work with trajectory optimization and custom contact implicit trajectory optimization solvers. And we put a lot of work into designing these beautiful gradient-based tools, and really thought like we've got like the best thing out there. We can do all this cool stuff. Then when I did my postdoc, started exploring some other directions, which are much simpler, which is just sampling-based MPC. So this is the category of tools that includes MPPI, predictive sampling, cross-entropy methods, and we're able to get really good results with this. So the first project that I did with that was this cube rotation, which is an imitation of an OpenAI cube rotation task. Now we have some GPU tools for doing this. Feel free to check them out. They're on GitHub. And this is just really working. It's super simple. I won't go through it, but you just throw spaghetti at the wall and you take a weighted average, and depending on what weights you use, you get different algorithms, but you're just trying things, you're sampling, you get different results. And it really works. We're able to get results that are competitive with old RL-based baselines that are, use a week of compute on a cluster, and we're doing just online MPC, and it's really simple sampling. And we're getting, this is mean rotations before a drop. So it's still not perfect, but we're at least in the ballpark of these RL baselines with a really stupidly simple approach. And this was kind of, to be honest, a little frustrating. I spent so much time doing these gradient-based optimization, really thinking through the dynamics, really like, okay, how are we going to best get the sparsity pattern of the Hessian? And then it turns out that you just come along and you sample, and it's just as good. So why does this work? Basically, you can think of all of these updates as approximating this sort of ratio of expectations, which is itself a score, proportional to a score for a certain probability distribution. Now, there's some things in the derivation I won't go over in too much detail now because we don't have time, but there you see this sigma squared there. That originally that was kind of frustrating because we have a score, but it's also scaled by something. Well, it turns out this kind of scaling is a standard guideline in your diffusion-based generative modeling. So that's kind of cool. It just falls right out of the math when you're deriving the score based on the sampling-based MPC, and it corresponds really neatly with the standard like heuristic-based guidance that people have come up with for diffusion models. So sampling-based MPC, we can think of this as online generative modeling. This process of throwing spaghetti at the wall and taking the weighted averages, really what you're doing is you're approximating a score function and then using that to update your samples. So we followed up on that by what we're calling GPC, which is Generative Predictive Control. And the idea is to train a flow matching policy based on purely simulation data, no demonstrations. So the idea is we run our sampling-based MPC, that gives us training data. Then we fit our generative model, and we can feed that data back into sampling-based MPC to get better data and better performance. These are all simulation examples. Here's our training data, that's sampling-based MPC. You can see the goal is super simple. Just go forward at a desired speed. It's not a well-tuned task at all, but it's kind of flopping around. It kind of does the right thing, but it's very random. Then we have our learn policy. It still is not the smoothest thing. I wouldn't want to run this on a robot, but it's really smoothed out a lot of the kinks in the training data, and you're able to make steady progress forward. We have some warm starting ideas that I'll skip from now. But turns out that this is really important if you want to do high rate feedback kind of thing. So this is balancing a double pendulum. So if you do warm starts, sort of inspired by the warm starts ideas that everyone uses in MPC, you can get a lot better performance. Here's screenshots of a bunch of trained policies and simulation. All of these were like under an hour on a desktop GPU, like a 4070, and we get reasonably good performance. The only one that's not great is the humanoid. Here's more numbers comparison. So lower is better here. These are costs, not rewards. But we compare with PPO, sampling-based MPC, GPC alone, and GPC plus, which is including the sampling-based portion of things. So you roll out a bunch of samples, including samples from the generative policy, and evaluate them. So in most cases, GPC and GPC plus are among the best. In the humanoid case, PPO is still outperforming our approach. Then when we go to GPC plus, we include the samples and evaluate the samples online, then that gets better. Warm starting is good. Okay, high level takeaways. Sampling-based MPC is generative modeling. To me, that was like a big insight, and I think that unlocks a lot of different interesting research directions. GPC complements behavior cloning. So this stuff with simulation that we're doing, it's really good for tasks that are easy to simulate but difficult to demonstrate. And so there are things that are fast. I don't know how to demonstrate a double cart pole swing up. I can't control that with my hand, but we can simulate it. And then with GPC, we can get a flow matching policy that's really good. On the other hand, simulating a bunch of cloth folding is going to be a lot harder. So that's probably a better place for behavior cloning. Still limited scalability, which we see in the humanoid. Lots of things we could think about, especially in terms of value function learning, to improve that. All right, I'll conclude there. Lots of open questions, lots of things to work on. What I hope you remember is that this is an awesome time to be in robotics, and things are happening fast. A lot of things are learning based, but for sure our model based and simulation tools still have a big role to play. With that, thank you very much. I'd be happy to answer any more questions.
Thank you. That's great talk. Can I quickly ask for the sampling-based MPC, you generate the data for your generative model policy training, but why is it go back again to the
Oh, good
sampling-based
question. Good
MPC?
question.
I didn't maybe follow well what happened there.
Yes, I was going quick, so good question.
Yeah.
So when we run sampling-based MPC, our original samples are a Gaussian around the previous input sequence, right? And then we take the weighted average, and that's what we apply, and we rinse and repeat. We could use a better proposal distribution, right? A more informative proposal distribution that's not just a Gaussian, but maybe something more interesting. When we train our generative model, that generates a sequence of actions conditioned on our observation. That's a more interesting proposal distribution. So we can mix in some samples from that more interesting proposal distribution and then get better performance. So then in iteration 2, our sampling-based MPC performance is better because we have a better proposal distribution. That means we have better training data, which in turn means that
I see.
Our model is better.
So you feed the generative model policy back to the sampling-based MPC to kind of reshape the distribution.
Yes.
And how like this loop, how you run this, you generate like just a batch of data sets, you train the generative model, and then you can how frequently you run this loop? Always kind of less frequent. You need to get good enough.
Yeah, good question. I mean, that's a hyperparameter, right? So I don't remember offhand exactly what we were doing, but you would, run a certain amount of time for a certain batch size, and then you train, and then you go back.
Yeah.
And it was, kind of like an RL iteration loop, where in PPO you collect a bunch of data, then you train, and then you collect and you train, sort of like that.
Cool.
So hi, I have a question.
Yes.
Yeah, so thank you for the great talk. And about the sampling-based MPC, my understanding is that you formulate the probability distribution of the ground truth solution as exponential of minus cost, which gives us the exact solution for the score function, which is gradient of cost. But
Right.
when we have constraint, you introduce some additional term which is represented by a Lagrangian. And in that case, do you also have a closed form solution for this probability distribution? Like, how do you? So only when we only have the cost, the distribution is exponential of minus cost. But when you have constraints, what is the distribution?
Yeah, good question. So I haven't done sampling-based MPC with constraints. I know people have thought about that question. It's an important one. And yeah, representing that constraint distribution is an important question too. The naive answer is that it should be an indicator function on your constraint. So you should only have probability mass when your constraint is satisfied. On the other hand, that might not be the best choice because your constraint samples, some of them will violate the constraints, and then you're just throwing them out. They're not informative anymore. So great question. I don't have a clear answer.
Okay, and also when you do generative predictive control, you adjust the sampling-based control with the neural network trained data model. And how do you incorporate the information, like with constraints or like adding some cost relevant to the trained model?
Good. Okay, so there are no constraints going on in here.
Okay.
This is just costs.
Okay.
And then the idea is instead of sampling from a Gaussian around the previous, you sample from your generative model. That's it.
Oh, but okay, but still Gaussian with bias mean or some random distribution. I guess random distribution.
Some other random distribution. So your
Okay.
your flow matching model generates samples from a weird distribution.
Okay, and start from that.
Yeah.
Okay, thanks.
I have a question. So, with the sampling-based MPC, with the generated model, you said that still in the humanoid task, it does not perform as good as PPO.
Yes.
So, what is it inside? Like, what do you think is the reason it
Great
cannot
question.
outperform?
I can speculate. I don't have like a hard evidence for this kind of reason. My speculation is that it's like a cursive dimensionality issue.
Yeah.
Because this is by far the highest dimensional task that we tried. I think the path that I'm interested in going to address this in the future is value function learning. And the reason that I think that might be a path to help solve this is that if you have a learned value function or you know the value function, then you can have a shorter planning horizon. And if you have a shorter planning horizon, then you have a lower dimensional problem. So that's going on in PPO, right? PPO has a learned value function. And so I think that is at least part of the missing piece that is allowing PPO to outperform us at this point.
Okay. So, in this setup, so the action space for the MPPI is still the joint, like target joint
Joint positions, yeah.
Okay.
Target joint position.
So, because like I think there is like in the MPPI for like quadrupedal locomotion, I saw one paper from CMU using like instead of directly sampling from joint space, they use like a cubic spline and then like sample in the compact like cubic spline space, and then later you interpolate back to joint space. So do you
Good.
think like redesigning the sampling space will improve performance in this case?
Yes. Okay. Two parts to that. Really good. Um, the first is the spline idea. So the splines is huge for this sampling-based MPC. So if I have 100 time steps of simulation, I don't want 100 samples. I want maybe
Yeah.
5 samples a long time. And so you can use a spline. And so we do that. We use a simple spline. It's just a zero order hole, but you could use a cubic spline or whatever. So that is really important. That's part of a larger conversation, which is about how do you reduce the dimensionality of the sampling space? And so splines is one way, but I think we need, for something like the humanoid, we need more. Maybe using task space, like something about the end effectors instead of joint space. Maybe that's an easy way to reduce the dimensionality. Maybe there are more clever, like internal embedding spaces that we can sample from that would be more efficient.
Okay, thank you. So another question is so here you try this humanoid stand-up, right? Have you tried a locomotion or like other
Uh,
humanoid task? What's
yeah,
the
haven't
what's the most
good.
challenging task?
I mean, I wanted to do the stand up because there's not like a predefined gate and it involves
Yeah.
a lot of like complicated contact interactions. So like their initial conditions were like random and just like fall on the ground kind of thing, and not just like stand up from lying down. Um, so that's why I focused on that. I think I haven't really tried it on other things. I think motion capture tracking would probably be a little bit easier, but still interesting. So yeah, I don't really know how it would compare to those other tasks. Good question though.
Okay, thank you.
So maybe a quick question, how you think this generative predictive model control the GPC you call can incorporate context model? I know this can be super challenging. And do you see there's a potential there, or this is completely open question?
Yeah, so the way that the contact model enters here is through the simulation. So when we're training, when we do run sampling based MPC, all of those samples are forward simulations. So in this case, we use Mojoko's contact model. You could use a different simulator. You could use your own thing that's really fancy, and that would give you different rollouts because the contact model is different and it would give you different results. So for sure, that's an important consideration. Like when you're doing model predictive control, the model, or in this case, the simulation, which includes the contact model, is important. Yeah.
Okay, I see. I guess it's a completely different way to handle contact than the traditional, trajectory optimization, CITO stuff. This is
Right.
kind of
And that's kind of
roll out, through the simulation using the
right. It's
sampling
kind of
method.
a really simple
So,
shooting based method.
so it's okay, I see. So it's kind of circumvents some of the bottleneck of the CITO, you know, traditionally, I guess this is
For sure.
okay.
Yeah, this is why I think it's so cool and also frustrating, right? Like it allows you to do contact implicit things. This is contact implicit.
Mhm.
But you're sidestepping all of those concerns of how do I take gradients through
Mhm.
contact, that sort of thing. You're just using samples.
Cool.
Uh,
Um,
I have
yeah.
kind of a question about mostly workflows with Drake. So we are longtime users of Drake in this lab, but I think when we started to work on learning project, the problem is that we found that it's hard to I guess integrate Drake into basically any of the learning pipeline. So I guess the question is just like where do you see like it's optimal workflow like which place is Drake like in this current generative AI workflow?
Yeah, really good question. Definitely the feeling at TRI and on the Drake team is that, yeah, we know Drake is not the tool for training an RL policy. right now. I mean, it's all on CPU. The focus has really been very finely on improving the dynamics, improving the fidelity, things like offline evaluation that are not massively parallel. There's strong interest in getting a GPU thing up and running at some point. It's not going to be tomorrow because they're very, careful about their code practices, and they want to make sure that whatever lands in Drake is really high quality. So at this point for workflow, if I'm training a RL policy, I'm going to use Newton or Warp or Isaac or something else, and not Drake. I think Drake still has it as it is today, still has an important role to play, especially in terms of validation. But yeah, it's not the tool right now for massively parallel simulation.
I have a question about that. So I think I saw like an NVIDIA Newton team is trying to integrate the Drake. So they said it's a Drake-like contact model. So my question is like is the TRI like collaborating with the Newton team to replicate the Drake in Newton simulator, or is it just NVIDIA try to replicate the Drake? Do you know anything about that?
There were definitely some conversations, and I don't know what the status of it is right now.
Okay, thank you.
All right. So I will maybe ask one last question. I think we already have good enough conversation. Once if you I think go back all the way to this scaling law figure about
Yeah.
the data gap. I think this, I'm curious. There's still, definitely there's a, I think 20% gap go all the way to, 100%. And we'll say the data gap, I feel it's not just about the data size. Even we have more data. Well, I guess I don't know even compared to this, GPT amount of data size. I don't know how many more years it's going to take for us to get a robot this size of robotics data, or maybe never. It's just very challenging. But in addition to the data size, I feel the data quality, I think matters a lot. I don't believe we'll just train the models similar to as GPT model language models did. I think robotic data is, I feel, fundamentally different. And so I think the data quality is another dimension. And then the data type, I think, also matters. Right now, I think a lot of data limited to you know, vision, this proprioceptive sensing data. But there are a lot of force data, I think, still missing. I know TRI has been work using this the bubble, right? The soft bubble gripper, and there are a lot of tactile sensing effort there. I don't know how much, kind of diversify the data types could be very helpful. I'm just curious in general, like your thoughts on, if you go back to the plot you have, to further push this task success rate, what other aspect you feel could be better, given your experience at TRA?
Yeah, I think that's a really good point. I think the data quality point is huge. I mean, that's something that I think everyone is finding out, that it's not just having demonstrations, but it's having good demonstrations that, cover an interesting space and show appropriate failure recovery, and that's really hard. Um, and yeah, to relate back to the GPC stuff, I think the training data we have there is based on random rollouts and sampling-based MPC. I would not call that high quality training data. I would consider that low quality training data that you can still get something out of, but it's much less efficient. It's much more difficult. And yeah, to the point about scalability limits, I think the quality of the data is really limiting us there. So yeah, agreement on all points, I guess.
Okay, cool. All right.
Can I ask one last quick
Okay,
question to
last question, please.
to
Yes.
yeah, just add on
Yes.
to that. Yeah, thanks for the great talk, Vince. And Yeah, just add on to the sampling based MPC. Because like for the reinforcement learning pipeline or something like the sim to real kind of technique, it's kind of more, well, this is like more well developed, but I want to see your opinion on like sim to real gap for like sampling based MPC, because I know you have a great work on like in-hand manipulation and but I guess like there's some other work on locomotion too, but I guess we're manipulation with like different kind of objects, like kind of sim to real, maybe even larger. See some of your opinions, maybe.
Yeah, okay. So just really quickly, I think the key thing for sim to real gap for sampling-based MPC is getting a state estimate. Because you have to start your rollouts from an initial state. So that state needs to be reasonably close, and that in a lot of cases that's pretty non-trivial. So with the cube rotation stuff, a lot of our work was not really the sampling-based MPC algorithm. That was easy, but getting an initial state estimate where the sides of the cube are not stabbing into the gripper, that was a big gap. And of course, there's simulation fidelity issues as well, but yeah, state estimate is a big thing.
Makes sense. Thanks.
Okay, all right. I think it's time to wrap up. And thanks everyone. Thanks, Vince, for giving this excellent talk. And yeah, good luck with your new faculty journey. And hope to catch up with you maybe sometime at the conference.
Yeah, sounds good. Thank you so
Yeah.
much for the invitation.
Okay. All right. Thank you. Take care. Bye bye.